I will be giving the lecture today on the quantum in pictures. Hello, everyone. Today I will be talking about spiders, which is the second chapter, the beginning of the second chapter in the Quantum in Pictures book. And I think I'll be covering 2.1 mainly. So yeah, during the talk, if you have any questions, feel free to interrupt and ask them right away. Or I can also leave some time at the end if you want to have more time for chat or questions. Okay, so that's all good. Maybe I'll start. So the topic of this lecture are these spiders. And so what are spiders? So in the previous lectures, you might have seen diagrams that you draw, which have some special kind of boxes and some wires connecting them. So in this lecture, we are going to focus on not just any box, but a special kind of box, which is called a spider. So what is a spider? So a spider is a box. It's also a generalization of wires. So a different way to think about spider is to say that, okay, if you have a wire, if you have two wires, and if I want to connect them, there's only one way to connect them. But with spiders, you can have multiple wires, and you can connect them using a spider. And here I will write a spider using this white circle. For people who are reading the book, this is usually green in color, but I think it should be just easier to do white and black. Okay, so let's define what a spider is. So a spider is a node with arbitrary number of inputs and output legs. So here I have a spider with 2 inputs and 2 outputs, but I can also have a spider with 3 inputs and 2 outputs, or no input and 1 output, or 2 inputs and no outputs, and so on. So you can look at like specific spiders, or 1 input and 1 output. So if I consider a specific spider like this, let's say it's a spider with 2 inputs, 1 output. In the bracket notation, this is same as saying I will give out ket 0 if both of the inputs are ket 0, and I will give out ket 1 if both of the inputs are ket 1. So in general, I can have, if I have arbitrary legs of the spiders, suppose there are m input legs and n output legs, this spider can be translated in the bracket notation as m inputs with n outputs of all ket zeros, or n outputs and n outputs of n and n m inputs of ket 1. So one thing this spider does is that it makes sure that all of the wires are carrying the same basis states. So considering a special example, if I have a spider like with 4 legs like this, if I know that this leg is ket 0, that means all of these legs will also be ket 0. Like this. Or if I knew that it was ket 1, then everything must be ket 1. So one way to understand spider is that it simply matches your classical, your basis states, your 0 or 1. Now, suppose we have 2 spiders. I'm going to draw it like this. Let's say I have 2 spiders, one with 2 inputs, 1 output, and the other with 1 input and 2 outputs. So what will happen if I connect them like this? Well, we can compute this using the bracket notation. So for this bottom one, I can translate it into bracket like this. So it's 0, 0, 0, plus 1, 1, 1. And when I compose it, when I connect the wire with a different spider, I can also write that spider here. So for this, it's two outputs and one input, so it's 0, 0. 1, 1, like this. And now if we expand the brackets, we can do a very simple computation and see that this is equal to, I'll just write down the four terms. So I'm just opening the brackets up here. So we get four terms in the output, like this. But if you notice that, okay, this term over here, now this is a zero scalar. So this term is equal to 0. And similarly, this is also equal to 0. And this inner product of 0, 0 states is equal to 1. And this is equal to 1. So if I remove all these 0 terms, what I'm left with is this is this bracket operator. So we can see that if I connect two spiders with one leg in between them, then that's equal to what I would have obtained by just writing one spider with two legs. Because remember that if I have a spider with two inputs, two outputs, that will precisely correspond to this expression. So in fact, this works even more generally. So if I have a spider with many different legs that's connected to another spider, which can also have an arbitrary number of legs, then I can fuse those spiders together as long as I make sure the number of legs are kept the same. So here there were 3 and 3, so I should in total have 6 output legs, and total number of input legs were 3 plus 1. So I should have 4 input legs. And this fusion would also work if you had multiple legs connecting two spiders. Okay, any questions so far? So yeah, this rule is called spider fusion.
Hello,
Yeah.
please bring down what is above there. I want to. Okay, like if I understand what's coming is get and what we get out is a bra.
Yeah.
And for the input, is it necessary like we should have a best state there, or this is an example you use?
Sorry, I didn't catch that. Can you repeat?
Yeah, you put 0, 0 and 1, 1. I'm asking if that is always the case, or this is just an example for the input.
So do you mean like in this example? In this example?
Yes.
So here, so this part was for there were two spiders, so one corresponding to, so I translated first spider as the bracket here, and the other spider as a bracket notation here. So for this concrete example of like 2 inputs, 1 outputs, and 1 input, 2 output spider that are connected like this, we obtained the result, which was this, which is same as the expression of same as the bracket expression for a spider with two inputs and two outputs. So it did not matter that we had a like the result here only depended on the number of input legs and number of output legs, and it again gives us a spider. Like, does this answer your question?
What I'm asking is, why do you use cat 00 and 11?
So, so see here, we got four terms by opening up the brackets, by composing these two spiders, which I've written in the bracket terminology here. And this expression was equal to this.
Okay,
And
thank you.
just by some simple calculation, we can show that like, so this term is zero, so it goes away. This term is zero, so it goes away. So we're only left with these two terms. And the scalar here in the inner product in between is just the same as 1 and 1. So we don't need to write it. So that's why we only have, that's how we got 0, 0, and 1, 1 here.
Okay. Yeah, I got the calculation, but it is fine. Yes, thank you.
Yeah, this represents the general rule of spider fusion, which says that if for any number of legged spider, as long as they're connected with at least one wire, you can fuse them. Okay, another property of spiders that's worth maybe pointing out is that if I have two spiders, if I have one spider with two legs and I swap them like this, that does not matter. Like, because it's just matching the basis, the cat 0 or cat 1, the swap doesn't make a difference. Similarly, if I have one input and two outputs, I could have also written it as spider with two input, one output with one leg bent up. So with these spiders, we can represent some interesting states. So states are things which have no inputs and one out and some outputs. So one such state is this state, which is a very simple state. But another state is a spider with zero inputs and two outputs, and that's actually equal to the cup state that you saw in the previous lecture. And you also have tests. So it could be like some wires with multiple inputs and no outputs. And in particular, if you have two inputs and no outputs, that's equal to the cap state. And using this, also one thing I can mention is that if I have a spider with one input and one output, that's just same as a wire. Now using this, we can actually prove the yanking equation. So the yanking equation says that if you have a cup and a cap like this, you can yank the wire. So to prove this, we can start with the diagram like this, and we can replace the cup and the cap with the spiders. And now we can apply the spider fusion rule. If you apply the spider fusion, we get this diagram, and we know that one input, one output spider is same as just a wire. So the spider fusion rule captures like more captures already some of the things that you have seen before. Okay, so here so far, all the spiders were of the same type, but we can make it more interesting. And in fact, to do quantum computing, you need more interesting kind of spiders. And to do that, you can allow labels on these spiders. So I can put any angle, let's say alpha, on a spider. And this corresponds to the bracket notation 0, let's say this is M outputs and inputs. Now, usually if we just have one spider with no label, this is what we get. But when we put an angle on it, that will mean you put this coefficient e to the I alpha between cat 0 and cat 1. These spiders allow us to do some more interesting things. But before we look at that, I think we can also now apply a modified fusion rule. So if I had alpha labeled spider and a beta labeled spider that are connected, when I fuse them, the angle will add up to alpha plus beta. And you can see why that might be. So the reason for this is that on the left-hand side, so from the left-hand side, on the scalar 1, sorry, on the bracket 1, I will get the coefficient of e to the I alpha. And from the right-hand side of spider, I will get a different scalar e to the I beta. And that adds up to, that gives us the phase of e to the I alpha plus beta. Okay, any questions so far? All right. So far we have been using a spider of the same type, the same color. But now to do universal quantum computing, you actually need two kinds of spiders. So I'll just repeat what I had here. So I have a spider labeled alpha for a white spider. But if I only have a diagram which is made up of the same kind of spiders, like whatever the diagram might be, I can always just fuse it into like one big thing. So there's not anything interesting you can do with this, except for just fuse everything. But to do something more non-trivial, we need something that doesn't just obviously fuse up. So for that, we need to introduce another kind of spider. And I will draw it with black. And this spider is called the X spider, whereas the previous one was I should have given the name. So that's called the Z spider. This is called the X spider. Sometimes this is colored red. So this was green just so let me remember. But yeah, I think I will go with the black and white convention. So to understand what this X spider does, we need to define, there is a question, I think. Okay. So now for this X spider, before I show what the bracket notation is, I can define first of all what two extra states. So we have the plus state, and this plus state is defined as some normalization in ket 0 plus ket 1. And I also have the minus state, which is defined as ket 0 minus ket 1. So it's plus because there's a plus sign in between and minus because it's minus sign in between. So now this X spider, instead of matching zeros and ones, it will instead match plus and minuses. So this will correspond to plus state. Let's say there's output and input. So, so it's on the plus and minus state, it's essentially behaving in a very analogous way to how it did with 0 and we can also allow the X-spider to have labels. So if I have an angle alpha, that will correspond to the same thing but with a phase. So we just put e to the I alpha in between. Now, this X spider behaves again like the Z spider in that it also has the same sort of fusion rule. So if you have any two X spiders that are connected with some connection in between, they fuse to become one big spider. And the angles also add up. Oops, sorry. Okay, so what can we do with these spiders? So one interesting thing that we can already do with this spider is that if I have a spider with no label, that's actually ket 0. So why is that the case? We can actually check that that's true. So an X spider is sum of like pluses and minuses like that. So, so if I translate this X spider to the pluses and minus notation, this is plus, plus minus, and that's equal to 1 over root 2 ket 0 plus ket 1 plus 1 over root 2 ket 0 minus ket 1. And that's, you can see that the ket 1 and ket 1 term will get canceled out because there's a plus and minus here. So this is the same as square root 2 times ket 0. And this square root of 2 is this coefficient that we don't really care about right now. So we'll just ignore it and we'll just say this is proportional to ket 0. And now if I had a spider labeled, let's say, pi or 180 degrees as they write in the textbook. So this will correspond to ket plus e to the I pi ket minus, and that's equal to ket plus, and e to the I pi is minus 1, so this is e ket plus minus ket minus, and that's equal to this. Now here you will have a minus sign. And that's equal to square root of 2 times ket 1, which is proportional to ket 1. So using these X spiders, we can actually represent these basis states, which are quite interesting. Now, what can we do with this? So if I have a, like now we can start talking about like more interesting kind of interactions when we have both Z and the X spiders. So if I have a Z spider like this, and if I input this X spider, so that's the ket 0, we know that, so this is same as ket 0, and we know that the Z spider, the white one, copies the zeros and 1 basis state. So this actually becomes 0 copied twice because we had 0, and this is the Z spider, which copies 0. So here we get 0 and 0. And similarly, we know that it also copies the cat1 state. So if I had the X spider labeled pi, that will also get copied. By the way, we are just ignoring these extra coefficients because they are not super important right now. So in fact, this rule also works. So this is called the copy rule. And this rule also works if you flip all the colors. So instead of X being copied, if I had this also is true. And similarly, if I had that's also true. In fact, anytime you see Z and X spiders, if you just change all the colors, that equation also holds. So these two are the copy rule. Okay, any question about copy or basis state so far? Yeah, then we can look at more interesting interactions of the Z and X spiders. So suppose we have this diagram where we have the X and Z. Oh, maybe I should mention one more thing. So here I only should copy with like 2 legs, but if I have a arbitrary spider with like many legs, and there's one of them is the spider, the X spider with no label, that will still copy. Like this. So you just need to make sure like the number of inputs and outputs are preserved, but otherwise it just gets copied. And same for all of the 4 I've written here. However, if the labels are different, so if I had a diagram like this, where I have some alpha, where alpha not equal to 0 or pi, then this is not copied. It's an important thing worth noting here. So this copy only works when the angle is 0 or pi. Okay. So suppose we have a diagram like this, where there are, instead of 1 leg connection between Z and X, there are 2 legs. What would happen now? So I claim that whenever you have 2 connections between a Z and an X spider, you can just chop those legs and write this as a diagram with the legs that are disconnected. So we can verify this. So the bracket calculation for, I mean, I think so the bracket calculation for this would go something like this, where you have 0, 0 plus 1, 1. And on this side, we will have plus, 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 and then minus, minus, minus. And and I won't do the calculation because it's kind of tedious, and I encourage you to verify this for yourself. But this is same as doing, it's same as this diagram, which is plus, plus, minus, composed with 0, Sorry, not this way. 0 plus 1. Oh, also there will be some factors of extra non-zero coefficients that I'm ignoring. So this is like not exactly equal, but up to some proportional, uh, some extra global scalar that we don't care about right now. So now this diagram is the right-hand side. So in fact, this is completely general. So if you have a spider with many legs that are connected by 2 legs in between, you can always just disconnect them. In fact, if you have multiple legs, let's say there are 5 legs in between, 1, 2, 3, 5, yeah, you can you can apply this rule again and again, such that you either have 0 legs in between them or 1 leg. So in this case, we have 5 legs in total. So there will be 1 leg remaining after I apply this leg chopping rule. Okay, any questions about this? So this rule is called leg chopping, or sometimes it's also called a hop in some literature. Questions about this? Okay, if not, then we can move on. There is a question? Oh, okay, I guess not. Okay, so now we can define. Oh, yeah. Was there a question? Sorry, someone was speaking. So I'll define a new kind of box. So here we define 2 spiders. Now I will define a different kind of box, which is called the color change box. And in quantum computing literature, this is also called the Hadamard gate. So the notation for this is, in the book, it's drawn like this. So you have this kind of box, and this box will only have 1 input and 1 output. And it corresponds to this bracket. So it will take 0 and send it to plus. And if you input 0, you get it plus. If you input 1, you get minus. So it changes these bases in a way. There's also a normalization here usually, which we don't need to worry about because we're only working up to global scalars. Oh, maybe I should have drawn this upside down. Oh, sorry, from bottom to top. Yeah, that's better. Okay, now with this, we can already notice some properties. So if I have this color change box, or maybe I should first explain why this is called a color change box. It's called a color change box because if I take a Z spider, I'll just choose, and I put this box on each of the leg of the Z spider, and you can see what it will do. So here's Z spider is matching 0s and 1s, but this color change box will change all the 0s to 1, all the 0s to pluses, and all the 1s to minuses. So this is actually equal to the X spider now. I similarly, if I had an X spider to start with, and I put this color change box, that's equal to the Z spider. So it changes the color of your spider from white to black or black to white. So that's why it's called that's why we call it the color change box. Now, some of the properties for this is if you have two of these in a row, that's equal to doing nothing. And you can see why that's the case. So if I have 0 here, then this changes 0 to plus, and this again changes plus back to 0. So it's doing nothing on 0. And if I had 1 instead, it would change it to minus, and this again changes back minus to 1. So whatever you start with, you get back the same thing at the end. So that's why it's equal to identity or just a wire, which is doing nothing. Any questions about the color change? All right. So in this picture, I just showed that, okay, if I surround a Z spider by all the color change boxes, I can change the color. Or here, if I surround all the legs of the X spider with the color change box, I get the Z spider. But instead of doing it like this, I can also use the fact that two of these form an identity to get a more dynamic view of how this works. So if I have a color change box here, I want to uh, show that I can push this through. So I can push this through to get X spider like this, and the color change box has now been copied to all the other legs. And we can very easily prove this because we know that this Z spider is same as the X spider, but surrounded by the color change boxes like this. So I only applied this equation from here. That's the one I applied. Oh, sorry, I applied not that one, sorry. This one. So I applied that equation. Now we know that two color change boxes in a row, that's same as identity, so it's just same as the wire. And we can get this. So in general, if I have a spider like this, where one, let's say one of the leg has this color change box, I can push that box through to all the other legs of the spider while changing the color. So this is like a more dynamic perspective on how the color change box changes colors. And if I had more spiders here, let's say I had a X spider that was connected like this, I can keep pushing this. I can now push, let's say, this color change box. I can push this color change box over here and here. So this would be equal to change. So here I have the X spider, so I change it to the Z and push the color change box like this. So you can always propagate these throughout your diagram. Okay, any questions about color change and how that works? Okay, if not, then we can look at an example of how we can use these spiders to do some interesting stuff.
Hello, sir.
Oh yeah, go on.
Please, does it mean that for the color change box to change the spider color, it must be applied to all the input and the output?
So yeah, that's true. If you want to just change the color, it should be applied to all the inputs and outputs, yeah. But if you don't have it applied to all the inputs and outputs, you can still do the color change, but you will get color change boxes on the ones that did not have the color change box. So maybe that's not very clear what I'm saying. Maybe we can look at an example. So suppose here we had a spider, Z spider, with two of the legs that had color change and two that did not. I can still apply the color change, but the only difference now is that the legs that did not have the color change box will now have the color change box.
Okay, so please, what if now this example is like half was having a more than the one that don't have?
Sorry, I think your
Like
voice
maybe,
cut off. Can you repeat that, please?
like please, what I'm trying to say is let's assume the legs are 5 and 3 of them is having the boxes.
Okay.
Can we still change the spider color from maybe white to dark?
Yeah. So if you had, let's say, 5 legs and 3 of them had it, you can still change it to from white to black, where you just push it on the legs that don't have.
All right, thanks, sir.
Okay, any more questions? All right, then let's look at an example of what you can do with this. So suppose you have a diagram, let's say, we'll just draw an example, a simple diagram that you might encounter in quantum computing. So suppose you have this diagram. So now this looks like a very complicated picture. But actually using the rules that we learned today, we can simplify this. So to simplify, we will apply the fusion rule and the leg chopping rule and see what happens. So first, I see that, okay, there are 3 Z spiders that are connected over here. I can fuse them together and all the angles should add up. So I will get one spider, again labeled alpha. And now it has 2 legs. Like this. I can fuse the X spiders here. So the black ones here I can fuse again. Using that will give me alpha connected to the X spider with 2 legs. And now we know that whenever we have 2 legs between Z and an X spider, we can simply chop them, which means this diagram, maybe I'll do it down here. This diagram, I can now erase the legs, and also we know that if I have a spider with 1 input, 1 output, that's just a wire. So I can actually also delete this spider. So that's just a wire connecting these 2 spiders. And now I can apply the same process on these wires on the right-hand side. So I can fuse these 2 Z spiders, and I can fuse these 3 X spiders and give me a diagram that looks like this. Two connections. Again, we can apply the leg chopping rule, giving us this in the end. But this 1 input, 1 output wire spider is just a wire, so I can write it also like this. So we have simplified a very complicated looking diagram to something quite simple, which is just 2 spiders on first and the third wire with an angle alpha and beta on it. So any questions about this? Okay, if there are no questions, then maybe I can give some more examples of example simplifications. Suppose we have a diagram which is
Please, can you go up small?
yeah, sure.
Sorry, please. How come the middle spider how did we lose the middle spider? Because I'm no more seeing it. We only have a line.
Okay, you mean the middle spider over here?
Oh, okay.
So yeah, there was a middle spider here, like this, that we still have after leg chopping. But we know that whenever we have a spider with 1 input, 1 output, that's just a wire. So what we did was we removed that middle spider. Like that.
Oh, okay. So we did not remove the first one because of the alpha.
Yeah, exactly. Because it's we can only remove, sorry, this is only true if the angle labeling this is 0. So if alpha, then this is not equal. Well, unless alpha equals 0. It's only true when alpha equals 0.
Okay.
Yeah. Yeah, thanks for pointing that out, because I think that was not very obvious. Okay, so let's look at a different example. Let's draw the. Suppose we have. Let's say this is more concrete. So suppose this is the diagram that we want to now simplify. So what can we do here? So the first thing which we can do is we know that any spider labeled by 0 or pi can copy through the spider of a different color. So here we have the X spider, which is black. The black spider can of label 0 or pi can copy through the white spider. So let's first apply that. So here we're doing copy. So that means we'll have two spiders labeled pi. Change box, and then the sides that spider. Next, we can apply spider fusion. So we can fuse these two spiders that are of the same color. And when we fuse them, the angles will add up. So we have pi and pi over 2, so we will get 3 pi over 2. Color change box, and then the Z spider. Now, what we can do here is we can take this color change box, and if we pass this up, then notice that the color of this black spider will become white. And there it will be a white spider connected to the white spider. So we might be able to fuse them. So it will be nice to get more simplification. So for that, let's push the color change box up, and that will change this to a white spider labeled 3 pi over 2, like this. And finally, there are two white spider labeled, two white spider connected to each other, so we can fuse them together. Okay, any questions about the steps here?
Hello. Hello.
Yeah.
Yeah, I want to ask, so the color change, I just want to establish the fact, so the color change doesn't change the value that has been given to the spider.
Yes, so maybe I should have mentioned that in the color change section. So here, if you have two spiders that are, if you change the color, so let's say the first one was labeled alpha, you still get the spider labeled alpha. So it only changes the color, it does not change the label, but it also works with any phase, any angle on it. Yeah.
Okay, thank you.
Yeah, that was a good question. Thanks. Any other questions? So yeah, feel free to ask any questions of if there's any of anything in the lecture. Okay. Well, if there are no more questions, then I guess this is the end of the lecture. But yeah, I'll stick around until the end of the hour if there are more questions. But, yeah.
Okay. Thank you very much, Razin. And so far as there's no other question, I think we can end it here. So yeah. Thank you very much again for honoring our invitation.
Oh, thank you. Yeah. Yes. Thanks for attending, everyone.
Okay. So participants, I think we have another lecture on Wednesday. So we'll meet you on Wednesday. The videos will be uploaded on the YouTube page, and the ones that are yet to be put on the platforms, we would notify them, put it on platform. So again, thank you, Razin, and thank you, participants. Hope to see you on Wednesday for our next section. Thank you.
Sorry, please, I have one last question.
Yeah, sure.
So from the spiders, if I to get one last thing clear, you change from the 0 states to the plus state, from 1 to minus, right?
Yes.
So does that mean you can liken the 0 state to the minus states because of the colors that you get? Can you liken the 0 state to the minus state? Because after you change the colors, you can now fuse the two spiders that have that same color. So can you
Yeah.
liken those two?
So can you what?
Make them like, are they alike, those states, the 0 state and then the minus state?
Sorry, I
Because after,
don't think I understand. Yeah.
okay, so after you change from, with the color change, after you change from 0, you get a plus,
Yeah.
and that is from like white to black.
Oh, yes.
And then when you change from 1, you get minus,
Yeah.
and that's black to white.
Right. Yes.
So
That's
that's
yeah.
so is because the 0 state is white, and then the minus is also white. Does that mean you can liken both of them? Are they alike?
Yes. Let's say you have a 0 state, and you put this color change box. That's 0, and you're applying this color change box over here, which means this gets transformed to plus state. But that the picture for this is that. So your question is, does that mean this is plus state? If I understand correctly, and the answer is yes. So this is how you write plus state, and this is how you write the minus state. Sorry, was this the question?
Yes, please. I wanted to know if I understand now. Thank you. I thought that the colors, the black one, maybe the black one is 0 and then white is 1.
Yes, that's true. So okay, so this is unfortunately can be very confusing if you see this for the first time. So the white one matches the zeros and ones like this, and the black one. So as you said, yeah, the black one would match the pluses and minuses. It would be plus and minus. There's some stuff here that I'm going to not write. However, this is not 0. This is actually plus. And the reason for that is if I have this diagram, what does this correspond to? If I write it like this, if this is 0, there is no inputs. Sorry, there is no input, so it's only output 0 plus 1. And that's equal to the plus state. So that's not equal to get 0, but it's actually equal to plus state. And
Okay, I understand. Yeah. Thank you.
Is that clear now, or maybe I can explain again? All right, thanks everyone.
Thank you.